So, good afternoon, everyone. Thank you very much that you are with us this afternoon. So, today we are starting within the framework of the course, the Applied Energy Systems, the invitation of experts all over the world regarding energy systems or energy format that the course contains. I think this will provide a more holistic approach of the course. More experts all over the world they are going to present in introductory way their expertise related to the course. So since this week and the weeks that they will follow, we are going to get involved about photovoltaics. It's a great pleasure to have with us Professor George Kakavelakis. A few words about Professor Kakavelakis. He has a bachelor's degree in material science from the University of Greece, then a master's degree in nanotechnology from the University of Crete, and a PhD in third generation organic solar cells. If we are talking about organic solar cells, this is the future of the photovoltaics beyond silicon, and he will explain to us why. Then he continued his studies and his professional work as a postdoc in the University of Cambridge. University of Cambridge in the recent world ranking of the universities is #1 in the world. So the expertise that will be brought from the University of Cambridge is something that we need to appreciate. He worked over there with graphene-based materials and graphene-based electrons, and we have discussed about graphene and the potential of the graphene. We are going to have more invited speakers in order to speak also about materials related to the energy. And then he moved to one of the, let's say, holy places about the ice and sea solar cells in Switzerland, in the university, in EPFL, in Lausanne, that he worked together with a chemist, Professor Grasser, and he was one of the nominees about the Nobel Prize in Physics. All right, so what is George going to share with us? I have informed him that you are in introductional level, so he's not going to use, he's going to tell you the story, and please give the physical meaning. And more than this, at the end of his lecture, please ask as many questions as possible. This is what I'm going to do. Who's going to ask more questions? All right, so feel free. With George, we are working together. We share our offices. Our office in Crete, which is a very good friend, but also he's an excellent scientist. So this is my main criteria, to invite scientists that they have an impact and they know what they are talking about in order to give you the perspective and give you another idea of what is happening around you. All right? So, George, the floor is yours. Thank you very much for your availability right now in Greece, 11 o'clock in the night. So I appreciate even more their participation. This is the challenge that I face in the US. We are 7 hours behind, and the others, it's very late. So we need to appreciate also their availability because this happens, for free under a volunteer base, and I would like you to grab the opportunity. Okay? So George, thank you, and you can start. Thank you very much.
Thank you. Thank you.
By the end of the lecture, I'm sorry, George, we're going to have a photo all together here. I would like to create my wall back in Greece with you, and also we invite you. Okay, thank you. George,
Thank you. Thank you very much, Kostas, for the kind introduction, and it's my pleasure and honor to discuss today with you this topic. This is an introduction in the third generation photovoltaic technology. So I know you have done some sort of introduction about photovoltaics, but I will give you a general overview, including first and second generation, and then I will jump to the third generation photovoltaic technology that is the topic of today. So, so this is an outline of my presentation. I will briefly give you the motivation of why solar photovoltaics, and then I will jump into the different generations, and also then I will discuss about the key figure of merits, efficiency, stability, and cost, and I will compare first, second, and third generation. And then I will discuss what is the added value that the third generation photovoltaic technology bring over the commercial technologies such as silicon or other second generation. And these include the tandem configuration. I will discuss this part. Also, I will discuss the added value of the ultra-thin materials and substrates that this device are built. Also, a very recent figure of merit that looks like very promising for third generation PVs, which is the power per weight figure of merit, or specific power, if you have ever heard, for batteries. And another recent term that is, they call this type of cells light cells, because they work not only with solar light, but with any light, including low intensity indoor lighting condition. And then I will summarize my presentation. So, on the first part of why solar photovoltaics, of course, we have all experienced, rapid growth of electricity demand, mainly because of the recent breakthroughs regarding fourth industrial revolution, as well as the population of our planet is increasing significantly the past few decades. So electricity demand will keep increasing with the future breakthroughs that are coming in the technology aspect. And this electricity demand is expected to be covered using gas, coal, nuclear energy, and renewable energy is expected to rise significantly the next 2 or 3 decades. Right now, the contribution of solar photovoltaics is only 2.8%, and this is mainly because it is on the early adoption curve for this kind of technology, because of several things that we will discuss later on. So keep in mind this number of around 3% of adoption so far. But in order to understand the potential of photovoltaic technology, we need to understand what is the resource that we have from our star, the sun. And if you compare the energy that arrives on the surface of our planet is enough, and I have done some calculations here, is enough to cover the human energy use for 1 year just by the exposure of our planet surface just for 1 hour. So imagine 1 hour of solar irradiation on the Earth surface is enough to cover the total electricity consumption for our total planet just in 1 hour. But unfortunately, so far we were able to, let's say, utilize only 2.8% of this total electricity demand. This is mainly because due to the early adoption of these materials and the let's say the things associated with the figure of merits of photovoltaic technologies. And another key thing that we need to think about is if we manage to cover, and of course we are not yet there on this, let's say, adoption of this technology. If we manage to cover some areas on the world map where we have like we have higher insolation from our sun, we will be able to cover the total electricity production and consumption for our planet. So definitely solar is very promising technology, and it has the potential to, let's say, cover the electricity demand and solve the energy crisis that arose after several catastrophic events the last few decades. Now, let's move. I hope that I managed to convince you that solar photovoltaic is a technology that can contribute to the energy generation as well as consumption problem. And now I would like to discuss the different kind of photovoltaic technologies that we have seen so far up to date. So, of course, this lecture will mainly focus on the third generation, but I want to introduce also first and second. So first generation photovoltaics include basically all the wafer scale technologies, including single crystalline silicon wafers, multicrystalline or polycrystalline, maybe you have heard, polycrystalline silicon wafer technology, as well as gallium arsenide. All these technologies are based on wafer scale production for this type of materials, and they are very thick and heavy. Okay. Um, all these type of materials and PV technologies, they have high efficiency but relatively high cost. Okay. Then the second generation includes different inorganic thin film technologies, and we will see later on a comparison of the thickness and what is the thickness of the wafers compared to thin films. But I will give you the order of magnitude for the wafers is approximately 200 to 300 micrometers, while for the thin films is less than a micron, approximately 500 nanometers. And the key message that I want to keep from this second generation technology is that they have lower power conversion efficiency as well as poor stability. And this particular one, cadmium telluride, is also a very toxic material that is, let's say, not very beneficial for the environment. Now, moving to the third generation, the topic of today involves solution processed materials, organic and hybrid materials, such as organic dyes, organic small molecules and semiconductors, quantum dots, and more recently, metal halide perovskites that we will discuss mostly later on. And these are some schematics of the different technologies from the single crystalline wafers to the thin films, the dye sensitized technology, and also the thin film perovskite technology. We will discuss mostly about those two. Besides categorizing this photovoltaic technology by the generation of, let's say, the inception of materials and devices, we can also, let's say, sandwich different types of materials and technologies, not only from, for example, combining first, second, and third generation, or first and third, second and third. We can combine the technologies in order to make the so-called multi-junction solar cell devices. This configuration has the following, let's say, idea behind it, that we need to stack different devices, different solar cells on top of each other. And the main requirement here is that they have a slightly different band gap in order to absorb different part of the solar radiation. For example, different for the visible, for the infrared, and for the mid-infrared photons. This I will explain you that will help us increase the efficiency of the photovoltaic technology by reducing the thermalization losses in the solar cell. I will explain you in a minute what it is about. Now, there is a very famous efficiency chart. This chart is produced in the United States, actually, in National Renewable Energy Laboratory. As far as I know, it is located in Colorado, in the United States. And here they report every advancement that has been demonstrated in any field of photovoltaic technologies. And the color gives a very nice, let's say, categorization. With the blue ones, you see the crystalline silicon technology and any crystalline silicon technology. And you can see here they have efficiencies of about 27%. Then with the green, you see the thin film technology. The maximum efficiency in this case is around 23%, while with the red ones, or yellow and red circle, you have the emerging PV technologies, including dye solar cells, perovskite solar cells, and organic solar cells, while in the yellow ones, you have the tandems, but the hybrid tandems, so combining two different technologies, while with the purple ones, you have the multi-junction 3-5 semiconductor. So you see a quite busy map but I want you to focus on this area where we have mainly silicon, third generation perovskite, and also here we have the tandems with the recent breakthroughs in photovoltaic technologies. So you see all these numbers. Maybe someone of you will ask me, okay, why they don't have 100% efficiency? Like, for example, uh, other type of devices that they have 80, 90%. Why they have 25, 26, 28? Okay. So now we need to discuss a little bit about the devices and the operation in order to understand the reason behind this very high loss from 100% to 25%. It means we have around 75% efficiency loss while converting light energy into electrical energy inside this type of device. So basically, a photovoltaic device converts the energy that any light particle holds into electrical energy through the phenomenon that is called photovoltaic effect. And the photovoltaic effect is basically the combination of two different words, photo from the Greek word phos, and voltaic, which is meaning of of the electricity, basically. So what is happening in this type of device? The sun or any other light source, I will explain to you later, is basically hitting the base, so the semiconductor material, in this case it is a silicon device. It excites electrons from the valence to conduction band, so this creates an electron hole pair, and as soon as these two charges separate, um, basically what is happening, there is a creation of voltage because the positive charge remains at the valence band and the negative charge is excited to the conduction band. So there is a potential difference. And as soon as we connect this type of device with an external circuit, we have a current flow. Sorry, we have an electron flow, and this gives rise to the creation of electric current. So, and practically, this is a nice schematic that I prepared for you, and this is practically what it happens. But of course, you need always to remember that our sun doesn't have a monochromatic light, so it carries different type of light particles in terms of energy. And here you see the distribution of different photon energies. And of course, the different, let's say, energy that each photon carries. Okay. So what is basically happening, depending upon this energy difference, the band gap within the semiconductor material, what is happening if the photon has enough energy, it can excite an electron from valence to conduction band, and this gives rise to the creation of the positive charge, the absence of electron. And as I mentioned, whenever this quasi-particle in semiconductor physics, it is called exciton, whenever this particle is separated, okay, there is a creation of voltage because we have a population of electrons in the conduction band and a population of positive charges in the valence band. And as soon as we connect our device with the electrons in the external circuit, the current starts to flow, and we have power production from this type of device. Of course, a significant portion of light from our sun doesn't carry enough energy, so the photons they don't carry enough energy in order to excite electrons from the valence to conduction. So around 30%, and I think I have it in my next slide. No, I have it later. A significant portion, around 30%, it doesn't carry enough energy in order to excite these electrons from valence to conduction, and this gives rise to a significant efficiency loss. This is around 30%, and another around 30% is because in order for the device to generate electricity, the electrons need to relax at the conduction band minimum. Okay, this is due to semiconductor physics laws. The electrons need to relax at the conduction band minimum. And you imagine we have a semiconductor material with around 2 electron volt, for example, band gap, and we have also photons with 3 electron volts. So it means it will excite electrons at deeper energy levels within the conduction band. And this energy is lost. Some portion of this energy is lost in order for this electron to relax at the value of the conduction band minimum. So this energy loss also constitutes about another 30%. And of course, we have also other efficiency losses related to, let's say, the purity of the material and also thermodynamics. Now, we can discuss a little bit more about efficiency, stability, and cost. These are the main figure of merits that anyone will ask and anyone will demand before photovoltaic technology is commercialized. And this is called the golden triangle photovoltaics. Okay, in order to commercialize a PV technology, at the same time, you need to have high efficiency, long lifetime, and very low cost. Okay, if these three are optimized at the same time, okay, the photovoltaic technology has a high, let's say, high potential for commercialization. And when we discuss about high efficiency, as I mentioned, around 30% is considered high efficiency. We need a stability of around 30 years, and a low cost means comparable with non-renewable energy sources electricity production. Okay. So now, discussing about state-of-the-art technology, silicon solar cells, they have like 90% market capture. So almost everything that you see commercially available and you can buy on the market is 90% is silicon. Okay, this type of devices they are around for more than 70 years, since 1950, and the recent development gave rise to an efficiency of around 27%. Okay, so this might not seem very high, but later that we will discuss, soon that we will discuss what is the maximum limit, you will understand that we are approximately reaching the maximum limit of this type of technology. Okay, and in order to characterize, so where does it come, this 27%? In order to understand and characterize the efficiency of a photovoltaic device, we need to measure the photocurrent that it produces versus the applied voltage. Okay, and this is a typical characteristic curve for the measurement of the efficiency, and the key figure of merits that you need to extract from this figure. Okay, it is the current that the device produces at 0 voltage, and this is called the short circuit current. What is the voltage that the device produces at zero current? This is the open circuit voltage. And also another figure of merit that is called the fill factor, and it's practically what is the maximum power output compared to the power output corresponding to short circuit current and open circuit voltage. So if you do you see my laser pointer?
Yes.
Okay, so practically, how can I calculate based on this diagram? I need to draw a square of the short circuit current to find the open circuit voltage, and I need to integrate this area. Okay, and then I need to integrate the area of the maximum power generation, and this is I will find it in this curve. This is the IV curve, and the blue one is the PV curve. Where the P is maximum, I can calculate the maximum power. And from this equation here, I calculate the fill factor, and from this equation, I calculate the power conversion efficiency. A stands for the area, and P in stands for the input power from our sun. This is approximately 100 milliwatt per square centimeter. Now, this was the efficiency of a single silicon solar cell, okay, around 20 by 20 centimeter. When it comes to a real solar panel, recent developments, we have around 24% power conversion efficiency in a panel size, and this 2 or 3% drop is due to electrical connection and also shadowing because of these silver lines that they have this type of devices. Okay, so now we need to understand if this 27% is good or not. Okay, and if we put all the math, I will not go through all the details because maybe we will need an extra hour in order to understand in detail this phenomena. Okay, what I have calculated here for you is the maximum efficiency. Okay, if we consider what the photons that they cannot excite electrons, so energy lower than the energy band gap, they are around 30.6%, so one third is already lost. Around 20%, 25% approximately are these thermalization processes that they occur because of the high energy photons. And we mentioned the electrons then need to relax at the minimum of the conduction band for the current to start to flow. Okay, so already more than 50%, and the rest is thermodynamic losses because of material and also the position between the solar cell and the sun, as well as the material impurities. So in total, this gives a number of 66.7% efficiency losses. Okay, so what is left is 33.3, and here is the maximum efficiency versus band gap, material band gap curve. And what we need to see, if we consider silicon, the band gap will be approximately here. So the maximum efficiency for this type of device is approximately 30%. And we have already 27. So if I'm not mistaken, we have already reached 90% of the maximum efficiency a silicon solar panel can produce. So in order to further improve, we need to either engineer the material to have a slightly different band gap or approach the problem on a different way. We will see later on how we can go from 33 even to 45 or 50%. Now, regarding cost, of course, the recent developments on materials and also the shift of technology to less, how can I say, energy demanding or with lower labor cost countries, the photovoltaic technology price dropped a lot, and nowadays, also considering the recent, let's say, energy crisis of oil and gas, nowadays it is considered very competitive compared to non-renewable energy sources, and that's why we see after the massive drop in the cost, we saw a very dramatic increase on the adoption curve. Now, regarding stability, you mentioned.
Sorry, just a moment. I mean, do you have any questions for the moment, or do you prefer to make the questions at the end? Probably at the end. Okay, George, continue. I just would like
Thank you very much. And last part regarding the key figure of merits is the lifetime. As I mentioned, you don't want to buy a solar panel and change it every year. Recent developments in materials demonstrate that even after 30 years, we can have a very small drop. We have seen around 0.45% is the state of the art right now, the efficiency drop per year. And if you do the math, I think it will give you around 13% drop after 30 years. So it doesn't mean that the lifetime is 30 years. It will have still 85% life, your solar panel, or let's say from 80 to 85. Okay. Depending upon the manufacturer, it will have around 85 to 80% efficiency even after 30 years. So it is a very, silicon technology, to summarize, is a very competitive in terms of efficiency, relatively low cost, and very stable technology. Okay, but you might think, okay, why this 3% is the adoption of this kind of technology? Of course, this is coming, this type of technology has some drawbacks. First of all, to make wafer scale grade silicon is a very hectic and very difficult process. It involves high temperature processing as well as very nasty chemicals. I will not discuss in detail all these things. But
George,
yes.
let me make a comment on this to the students in order to connect with the first. Sorry, I'm sorry that I interrupt you.
Yes,
This
no
is
problem.
like why we have a minimum CO2 production regarding solar cell. However, it's the lowest one compared to all the renewable energy sources. The main reason of this amount of CO2 has to do with the production of the wafers and the production of the device. And this is the reason. Okay? So thank you, George, and I will never interrupt you again.
Thank you very much for the comment, and I think I will connect this comment with my next transparency. So thank you very much. And exactly right after Costa's comment, we see what is the carbon footprint compared to so very spot on comment, different type of electricity production, and we see among all the different renewable energy sources, photovoltaics, because of silicon, they have the highest footprint. Okay, so even though it's a very clean technology during operation, during fabrication, it is by far the worst in terms of carbon footprint. And this is mainly because of this process that involves the creation, the production of wafer scale silicon. And before, let's say, 30 years ago, that the third generation photovoltaics were invented, 1990s, and the efficiency of these devices were not so high, the stability was not so good, the cost was very high. If you see, for example, this curve here, 1990s was very high, around $5 to $10 per watt, extremely expensive. The scientists thought the idea, is it possible to capture sunlight with a more sustainable and high throughput method? And let's say the answer was very obvious, but very few of the researchers were able to see it. And the answer is very simple: photosynthesis. Everyone knows that this process is mandatory for human life, but a few of them realized solar panels based on this type of method, based on this type of approach. What is practically happening in photosynthesis? Very briefly, sunlight is absorbed in the leaves of a plant, and during the process, CO2 is captured, and together with the oxygen from the environment and the humidity, there is a production of sugars that feed the plant. Okay, if we do some calculations, this will, if we manage to make this process very efficient, so practically 100% efficient, it will solve the electricity demand problem. It will give rise, this is some calculation we have done, 95 terawatt electricity production. And you remember the total electricity production and demand is around incomparable to this number. Okay, and in practice, back in 1990s, I will explain you briefly here. People from Switzerland, Professor Michael Gretzel, he invented a device that mimics this process, photosynthesis. So it was called first photosynthetic cell, and nowadays it is called dye-sensitized solar cell. What is happening? We have a semiconductor material like titanium dioxide, but this material does not absorb visible light, so it is coupled with a material, a dye, an organic dye that absorbs the solar light very efficiently. That's why it is called dye sensitized, because the dye is sensitizing the semiconductor in order to absorb the solar radiation. Okay, and then these people were very lucky because these particles, titanium dioxide, they didn't know so far, but now today we know why this device works because these particles, they only accept electrons. So what was happening? Solar was exciting the dye, then the electron was excited and was transferred to titanium dioxide, then was transferred to a conductive oxide, transparent conductive oxide, and then what was practically happening? The electrons were extracted to the external circuit. Another electron was then injecting back the electrons through a liquid electrolyte, like what is happening in a lithium-ion battery practically, is a very simple, similar operation. And the electron is now regenerating the dye through the electrolyte. And this process can happen millions of times, and these devices are very stable and of high efficiency. So this is the, let's say, the closest to the photosynthetic process, okay? And this is a typical dye-sensitized solar cell, so the first third generation photovoltaic technology, okay? And you see different colors because we have different dyes with different absorption bands. Okay, so you see the yellow dye, the blue, the green dye, you can do blue dye, even dark dye to absorb the whole electricity. Okay, very nice demonstration. And what was very surprising at this point was that if you had a flat, okay, area of titanium dioxide, the efficiency was very poor because the dye was only absorbed on one surface. But if you were making this titanium dioxide as a mesoporous layer, you were able to increase the surface area, the dye was absorbed in a much higher volume, and the efficiency of the device, so in this case, the quantum efficiency, which is the number of photons that are created to electrons, they went up from 0.1% to close to 90%, which is comparable to what silicon solar cell can do. And this was amazing because you imagine the thickness of the dye here is self-assembled of 2 to 3 nanometers. So with 2 nanometer thick semiconductor, you can have 90% quantum efficiency, and for silicon to do so, you need 100 to 300 micrometers. Can you imagine how groundbreaking this behavior was? And this was several times nominated for the Nobel Prize. The Nobel Prize was given to lithium-ion batteries a few years ago, and that's why I believe they will never give it to dye-sensitized solar cell because the operation is very similar. Okay, and practically the second generation dye-sensitized solar cell, okay, or let's say the next breakthrough came from a Japanese group many years ago, and they replaced this dye, the extremely thin organic dye, with another crystalline material in this case, and they managed to open the path for high efficiency photovoltaic devices based on this configuration, because this configuration gives high quantum efficiency for specific wavelengths, you see from 450 to 700, but the problem is the rest of the photons of the of the sun are lost, okay? So practically what this group did is to engineer materials that they work on a wide range of solar photons, okay? And they open the path for highly efficient devices. These devices' maximum efficiency today is around 13%, 13 to 14%. So practically, why these new materials to replace the dye are so important? Because practically they combine both worlds of organic and inorganic semiconductors, so the dyes and the silicon materials. And why so? Because they contain both organic and inorganic species. Practically, this is the crystalline structure of the perovskite materials, and they have a typical formula of ABX3. So for every A cation and every B cation, you have you have 3 anions, okay? And you can use different kind of a cation such as cesium, which is inorganic, and methylammonium formamidinium, this is organic cations, for the A side, these uh, red circles. Okay, typically for B, we use lead. This is one of the key drawbacks for perovskite because lead is toxic. But we have for many years lead acid batteries and we still use lead acid batteries, so I don't think it's a big of a deal. And for X, we can use either, these are halides or iodide, bromide or chloride. And you see that by changing the composition, we are able to tune the bandgap of the material, a property that with silicon we cannot do. And we know that in order to improve the efficiency of silicon further, or photovoltaics further, we need to make the bandgap close to the ideal 1.4. Okay. So we went from the dye-sensitized solar cell to the perovskite solar cell device configuration. These are figures extracted from a recent paper we published together with Kostas. And the typical operation of this kind of device is that we have a transparent oxide, conductive oxide. We have the same electron transport layer, the material that accepts the electrons from the semiconductor. We have the perovskite in order to absorb the solar light. We have a p-type material that plays the role of the liquid electrolyte, but in this case we have a solid state material, and instead of platinum we have gold. This is another drawback, it's very expensive. So practically what is happening, the light goes through glass oxide and titanium oxide. It excites electrons from the valence to conduction, and then electrons are flowing towards one electrode and positive charges towards the other in order to create electricity. Okay, why these materials are so, let's say, desirable for solar cells? Because they combine, as I said, both worlds of organics and inorganics. So they are both solution processed. We can tune very easily the bandgap, but at the same time, they have very strong absorption coefficient. What does it mean? With a specific thickness, okay, we can absorb very high. For example, with silicon, we need 100 micrometers or more, close to 300 micrometers thick slab in order to absorb 100% of the incident light. But because of this 1 to 2 order of magnitude absorption, improved absorption coefficient for these materials, they can absorb the same amount of light, close to 100%, even with less than 1 micron. So we have a 3 to 500 times thinner material and device. And this translates to significantly lighter devices and flexible devices. I will discuss this later on. Okay, and the other benefit is we don't need anymore these nasty chemicals and high temperature, etc. We need to mix these precursors in a typical solvent and then deposit the device, the materials, with very simple techniques. And this can even involve and include inkjet printing, like the how we print the newspapers, or spray coating, and other type of techniques that all of them occur at room temperature, and the material is crystallized at very close to 100 degrees C. We don't need 2 to 3,000 degrees C as in the case of silicon. In this case, we need 100 degrees C in order to make the full device. So what is happening? We reduce significantly the carbon footprint of the device.
And not only this, George, also the energy demand. Because the higher the temperature, the more demand we need to, more thermal energy we need in order to produce. Remember, thermal energy is like analog to KT. K is the Boltzmann constant, T is the temperature. So the higher, the more the energy we need, so the more CO2. Thank you, George. Sorry.
Thank you very much. And as you can see in this energy map, by engineering the materials, these are the perovskites here and at this side, by engineering the materials and the different anions and cations, what we can do, we can tune the bandgap. You see, we have 1.5, 1.4, even wide bandgap, 2.2, and this you will see why these materials are very beneficial. even the wide band gaps, you will see later on. So by tuning this composition, we can fine tune the energy band gap depending upon the use of the device. And now I mentioned 15% for dye sensitized solar cell. Nowadays, state-of-the-art perovskite solar cell uh, has surpassed 26% power conversion efficiency. 26.7, as far as I remember, is the recent world record. So practically has the same efficiency as silicon solar panels, even though this material is approximately 500 nanometers thick instead of 3 to 300 micrometers that we need for silicon. You understand the material utilization efficiency that we have here. Okay, and this is finally the, let's say, efficiency map that we have. And of course, you saw that we didn't discuss this material that depicts the highest efficiency, because these type of materials are very expensive and they are used only for space applications, because they cost like 10,000 US dollar per square meter. They are extremely expensive and they cannot be used for commercial use. But you see nowadays that perovskite and silicon, practically they have the same efficiency. So, okay, now one of you will ask me, okay, problem solved, let's commercialize. Not yet, because these materials come with some problems, because they are produced at such a low energy and very easily. At the same time, they also decompose very easily. So they have a very, let's say, poor stability against environmental conditions, and research is currently ongoing in order to solve this problem. This is the key problem. And the second problem is that they involve gold, that is very expensive, and it is evaporated through thermal evaporation. So these two problems are the key ones. Stability is improving through encapsulation and other methods. And also this problem with gold is currently an ongoing research to replace gold with other materials such as carbon, graphite, even graphene has been applied recently because of its very high conductivity. Okay, and according to theoretical calculations, if you manage to make this type of devices with carbon electrodes, okay, and still maintain, what happened? Come on, okay, and still maintain this 20% on the module, on the panel size, you will manage to drop the cost or to reduce the cost of the solar panel by a significant number, and this will give rise to a rapid commercialization of this technology. And this practically is one of the first solar farms that I ever created. This is located in China, and each panel contains 96 of these perovskite modules, and this, as far as I remember, is a series of 7 solar panels, each one containing 96 modules connected in series. Okay, so we see scalability is ongoing, research regarding efficiency is ongoing, and everything looks bright, but we need to further improve stability and get rid of gold. Okay, now on the remaining time, I will try to a little bit speed up in order to explain you also added value, because so far we compared perovskite dye sensitized with silicon. But what is the added value? Is there any added value that this type of devices can present? And I have all these things I want to discuss. I hope that I will manage to do. Okay, the first part that it wasn't able before this third generation solar cell is to make a very efficient tandem cell based on silicon. Why? Because all the materials, all the semiconductor materials that they were available before perovskites, they couldn't provide a highly efficient wide bandgap perovskite. And so, someone of you might ask, why wide bandgap? Because in order to make a tandem device, we need one cell to absorb at a specific range, like the silicon does, the blue one, and the other to absorb on a let's say, complementary range, like this 1.6 to 1.8 electron volt band gap semiconductor. And what will happen if you engineer the material very well? What you will reduce? You will reduce the thermalization loss, because if all these photons go just to silicon, the silicon device has a low band gap, so the blue photons will excite a lot of electrons at the deep level of the conduction band. So this will give rise to low efficiency on silicon solar cell. On the other hand, if we use only perovskite, we will not be able to capture all this area, because the perovskite has an absorption profile that stops around here. But if we merge these two, we will be able to achieve significantly higher efficiencies. And if I manage to go, yes, according to theory, okay, the maximum efficiency for this type of device, perovskite silicon, is approximately 45%. And indeed, so far, we have managed to achieve close to 34%. So we are very well on track in order to. So we have already broken the Shockley-Quasar limit, of course, this is for the single junction, which is 33.3. We have managed to break through this efficiency limit, and we are going all the way towards 35% efficiency very soon. Okay, but good news is that we can couple the perovskite not only with silicon, but with any other photovoltaic technology that has similar band gaps, such as silicon, such as cadmium indium sulfide, which has also 1.1 eV. And good news, what we can also do, we can also make low band gap perovskite materials. If we engineer the materials, we can make low band gap perovskite to absorb in the same rates as silicon, and still use this wide band gap perovskite and make the so-called perovskite tandem device. And as you can see here, the maximum efficiency these devices can produce are approximately 40%, as far as I remember. And so far, we have managed to achieve 30% in the literature. So also this direction is going very well. And the perovskite material is an enabler for high efficiency tandem devices in order to break the efficiency limit. Now, let's move to another aspect that was overlooked and very recently um, uh, beyond efficiency research is very active on it, and this is in order to exploit the property of the ultra thin behavior of this type of devices. As I mentioned, you see here, and I will explain to you a little bit better now. These silicon devices, they have 200 to 300 micrometer thick silicon wafer. Okay, they can be produced a little bit thinner, but it will be with the cost and the efficiency. Okay, so this is the limit, okay, the range in order to achieve these highly efficient silicon cells. While for our emerging perovskite devices, we need just 500 micrometers. And once again, I will explain it. We have materials, okay, like this one, for example, the perovskite, this methylammonium lead iodide, that absorbs the incident light, the incident solar light, very efficiently, significantly more efficiently than the crystalline silicon, and even better than the state-of-the-art gallium arsenide material. Okay, this provides a slightly better efficiency because it is a crystalline, single crystalline wafer device, but it's so costly that we don't even consider it for commercial use. Okay, and why this is important? This light and extremely thin device, because practically we can integrate, and these are real integration of devices, into any substrate, any surface, even curved, even on extremely, let's say, fragile substrates. We can integrate everywhere these devices, and we can make them flexible because this material is polycrystalline, is thin, and it will not crack even if we make it flexible on a curved substrate. Okay, we can integrate into planes, into satellites, into sail, into wearables, okay, into electric cars. Okay, and this will revolutionize not only let's say like the solar farm that is happening regarding electricity production, but also portable uh, electricity demand.
George,
Yes, please.
can I ask you something as an order of value?
Mhm.
How heavy is a battery?
Like a 500-watt silicon
Oh,
panel, it is more than 15 kilos.
no, a battery that we are using in our car. How heavy is it?
Can you repeat the question?
The battery that
Ah,
we are using,
the battery. Oh, in an electric car, you mean?
an electrical one. How heavy is
In
it?
electrical, it is like one ton.
1 ton.
Yeah, yeah, it's extremely heavy because for an electric car, you need like a 100 kilowatt electric battery.
Right, and how heavy it would be a solar system that can provide all this energy?
No, I mean with for this type of solar panel, you cannot replace completely the car. You can extend the range.
All right, okay. Thank you.
This is for some additional energy in order to extend the range of the car. And this
Okay.
practically commercial examples already exist. I don't remember exactly the brand, but they already exist some brands that they have integrated photovoltaic devices.
Looks like Volkswagen.
Maybe, I'm not sure. And I think this is one of the future uh, potential markets for this third generation photovoltaics. And something that is connected with this part, but also mainly related to the space travel, okay, is the weight of the panel, okay? Um, because in order this is a graph from NASA, as I remember. In order to launch uh, like a space mission, even at low Earth orbit, okay, you need thousands of dollars per kilogram of material that you want to be to launch on even on a low Earth orbit. Okay, so imagine that you want to build, for example, and Elon Musk, a very bright entrepreneur, he wants to build uh, uh, he wants to populate different planets such as Mars. Imagine the cost that will bring, yeah, just to populate the planet with solar panels to provide electricity. Yeah? And imagine to make this using heavy panels. It will be of a very high cost. But if we manage to use the emerging photovoltaic technologies, yeah, because of this specific figure of merit that is called power per weight or specific power, and what it is exactly, it is how much power output, the device will produce at a specific weight. For example, uh, watt over gram or kilowatt over kilogram. Okay. And we have done some calculation, and this is a paper that we published a few years ago. And according to the literature, uh, you see, for example, for even for extremely thin silicon, I don't remember where it is. It is somewhere.
That
Yeah.
thing,
Even you see, for crystalline silicon is zero point 0.5 watt per gram. For extremely thin amorphous silicon is around 5, while for perovskite and other emerging photovoltaics, it can reach even to 30 watt per gram. And this is experimental. It's not like what is the theoretical. So you see already two orders of magnitude better than crystalline silicon. Okay, so there is a significant potential for commercialization. And this is mainly because of the thin perovskite thickness, but as well as on the integration of extremely thin substrates. And here are some examples like polyimide, PDMS, you see curved substrates. And here, for example, you see a very nice uh, example of a very extremely thin integration on a 1.4 micrometer substrate. Imagine. So the total thickness of this device is less than what it is. It should be less than 3 to 4 micrometers. And this device, imagine or not, it is integrated on a soap bubble, and the bubble remains intact. And this is a real solar cell. Okay, imagine how lightweight this type of device it is. Of course, not to mention they are extremely durable and versus bending, and they are very flexible because of this extremely thin nature, and they remain almost intact their performance even after thousands of bending cycles. Okay, and I will skip this part and I will go here to show you that we have done also a calculation, a theoretical calculation, and we have seen that if we manage to use extremely thin substrate, okay, like this one of the 1.7, okay, keep this in mind, and we manage to have very high efficiency, so to keep this 25% efficiency, this will give rise to a theoretical level of approximately 8 watt per gram. And you remember the value for crystalline silicon or other devices is less than 0.1. So it is a really breakthrough, a game changer regarding the power per weight figure of merit. And then give me like 2 or 3 minutes to finalize my talk. I think I will be on time. To give you the introduction of light cells. Now, so far, we know the term solar cell, but recently it was introduced the term light cell because these cells, these devices, practically, they don't work only with solar light. They work with any light, including indoor. Okay, and practically, what do you have in your room? I'm pretty sure you have a very modern building, and you have LED light bulbs inside. I think so. What practically happens? Here is the wavelength dependent energy distribution of the solar of our sun. This is the incandescent, like earlier previous generation bulbs, halogen, fluorescent, and now we have these modern cool white LEDs that they have emission from 450 till 600, and the warmer that they have slightly shifted emission. Okay, so if you are using with this type of LEDs, that they are also extremely low light intensity. If you use a silicon solar panel, we have seen some recent work. We have done some research recently. We have seen that even with silicon solar cells, that they are very highly efficient on solar light. They can produce only 10%, while use wide bandgap perovskites. You remember that we can do this very easily to match the maximum intensity of the white LED that is approximately at, I would say, 1.8 electron volt. That is matching also the wide bandgap materials that we use in the tandem devices. Efficiency of more than 35% have been reached for indoor lighting, and this is very beneficial in order to use it as a power generator for low electricity consumption devices such as sensors and other IoT devices. And we see here a very nice map of what this type of devices, they can work both very well for outdoor in order to provide high power, let's say electricity consumption devices, as well as they can work with the indoor lighting in order to provide electricity to sensors and other IoT, NFC, like smart devices. And this type of behavior can only be, this type of light can only be captured if you use this third generation photovoltaic. So this is also a game changer regarding indoor lighting. And they are already commercial products. There is a company in Sweden called Exeger. You can go and have a look. They have already integrated solar panels for different types of electronic application, and you can always charge your battery either indoor or outdoor using their photovoltaic technologies. So I think that's it for my presentation. I hope I covered the third generation photovoltaics. I did some general overview about first and second generation. I compared and I did the benchmarking of the third generation with commercial technologies like silicon. And also I provided you some overview and some guidelines of what will be the future research direction of perovskite and other third generation photovoltaics, including the tandems, the ultra thin, the lightweight, the power per watt figure of merit, and the indoor lighting condition. Thank you very much. I hope I didn't consume too much time. And yeah, thanks a lot for having me and I'm ready and very happy to reply to any question. Thanks a lot.
Thank you very much, George, for the presentation. Now I would like to give the floor to the participants. If you have
Should I stop sharing or not?
yes, or you can leave this transparency. Anyhow, you are going to share with us the transparency in order to share it with the students through their platform. Any questions? Any kind of question? Yes, sir. Introduce yourself.
Hi, I'm Matthew. I just wanted to ask, the main challenge with emerging technology, the emerging material, is it the stability of them? So like for like perovskite, I forget that material. Is it the stability and the durability of it? Mainly, that's the main challenge.
Thank you very much for the question. Yeah, I mean, as you have seen, the efficiency of this type of devices is now on par with silicon, so there is no problem regarding power conversion efficiency. The main issue and the main research direction now is how to solve and improve the stability, how to replace expensive metals like gold, and also how to scale up, because silicon, with silicon industries, they have the know-how how to scale up to terawatt production per year. For perovskites, there are some startups in the US. You have a very active perovskite community, and there are several, of course, in China as well. And there are several startup companies of the 100 megawatt production scale capability. But of course, if you compare it with the gigawatt or terawatt for silicon, it is very far away.
Thank you, George. Thank you for your question. Any other question? Yes, sir. Introduce your name. Is not going to remember. This is the. Please go ahead.
I'm Jonathan. On the carbon footprint figure, it had something called solar CSPs. I was just wondering what that was.
I'm sorry, I cannot hear you very clearly because you are a bit far away. Or either come closer to the microphone or, yeah.
Matthew, am I right? Matthew.
I'll talk to you. Jonathan.
John. Yeah. Yes, please go.
I'm Jonathan. I was just
Hello.
wondering there's a carbon footprint figure and there's a thing called solar CSPs. I was wondering what that is and like what the difference is between regular and solar.
Okay, let me go back just a moment.
And share your screen. Thank you.
Yeah.
You can share your screen again, George, in order the Jonathan to.
Yes, I will in a minute.
It was where the camera.
Do you mean this transparency?
Not this one. Now you are in conclusion.
It was that figure.
Go back to the figure, please. Footprint. CO2 there.
Yeah.
Can you make it full? Excellent. So it's a solar CSP. What kind of technology is this? It's a concentrate, I think.
This is the concentrated systems.
Let me speak to you. This is mainly in order to convert the light to the thermal energy, in order to make steam, in order to generate mechanical power for engines. All right. So the photovoltaics are the conversion of light to electricity. The concentrate solar panels. Well, this is like concentrate solar panels in order to heat water. The water creates steam, and the steam pumps engines in order to move. So it's like the conversion of light to thermal energy. All right.
Yeah, and because the They work on such a high light intensity condition. They produce significantly larger amount of power, and that's why the number here is significantly lower. But the cost in order to make these devices is higher. So at the end of the day, there is a trade-off between cost and carbon footprint.
And also they're using mirrors in order to concentrate. I will show you a facility in the Negev desert in Israel, but they have all, very big curved mirrors. They concentrate all this light from the desert. They cut it into the fiber, and then they can send it wherever they want. So it's a simple as an idea, but with a great impact. Thank you, George, and thank you, Jonathan, for the question. Very good question. Any other question? George, in between, I would like you to highlight a figure that I think that it's important for our students to remember. What is the total thickness of the active material regarding silicon solar cell, and what is the total thickness of single junction organic solar cell?
Okay, the thickness of the silicon.
The active material. I'm talking about the active material.
Yeah. The active material, the silicon wafer, it is around 300 micrometer.
For silicon.
For the organic solar cell is like 100 nanometer. For the perovskite, it can be around 500 nanometer.
So do you understand the difference? The one is like 300 nanometers for silicon. Am I right?
300 micrometers.
Micrometers, yes, correct. So we are talking about 10 minus 6 for silicon, so much material, and for the other roughly, we are talking about 10 minus 9 thickness. And this shows the less the material, and we have the same efficiency. And at the same time, the weight is much less. So can you understand the impact? That's why they place it in the solar, because the future of the panels, to be honest, is like, of course, the power of areas, the rural areas that they don't have, they cannot cover, the cost, which is free. You told me, in the previous course, but also the space, so they can lift, whole satellites with much less weight in the same fuel. It's more efficient, even in your car. That's why I asked them about the batteries, how heavy they are in the electrical cars. 1 ton. That's why batteries, they have no future for the electrical. Now they're talking about hydrogen because of the weight. Imagine now that the solar panels with such a low weight, George mentioned very well the power per weight figure. This is the future. Performance and weight, because weight is related with energy that you need. And energy is cost. All right? So think, this is like, another perspective. So for silicon, if we're talking about silicon solar cell, something generates the technology of 1960s, 70s. Of course, it's a bottom, it's very mature. Everything should be around silicon because all the infrastructure, all the industry is based on this technology. So we need to integrate new technology within the same infrastructure in order to be attractive and Elon Musk very much. All right? Any other question? Thank you very much, George. It was important. George, I would like, in order to close the photo with the student, I would like to tell us as well, what is the main challenge? At the very beginning of your talk, you mentioned that even though solar light can satisfy the human needs within a day, but still we are far away in order to integrate this technology and cover all our energy needs with a very green way. What is the main challenge in order to go to this level? Because we know, for example, the geothermy, Iceland covers everything with geothermy energy. That's why Google servers are there. But what is the main challenge regarding the solar? Thank you, Joe.
I believe the main challenge is batteries. It's not the solar, because at the end of the day,
storage of the energy.
Yeah, the storage of the energy, because solar panels are very cheap, but the problem is they don't work 24/7. They work, I don't know, maybe depending on the geographic location, from 5 to 7 hours per day.
Okay.
But regarding technology, I think scalability. I mean, we are not there yet. We need to create more gigafactories in order to cover the demand.
Okay. So, thank you, George. Any other question? I'm looking for my mobile phone. All right. So, do you mind, George, can you wait for us?
Yeah, no problem.
Do you want to put a photo? Sure. All right, let's go, because I want the photo of you as well. So this is over your mind. And if you have a Facebook, let's add the friend 100%. Thank you, George. Cowboy. One. My iPhone. One. I think it's mine. 1, 2, 3. Wait for me. 1, 2, 3. Okay, thank you. Thank you very much. And we'll speak on Friday. So on Friday, I will recapture a few things of what George has mentioned in order to continue with the fundamental. George, we really appreciate and have a
Thank
nice
you, guys. Take care and enjoy the rest of the day.
Thank you.
Bye.
Thank you, George.
Bye bye.